Hello, everyone, and welcome to the third lecture of Inorganic Chemistry, in which we're really going to deep dive into the last step of understanding how transition metal complexes actually bond, which is the ligand field theory. Now, what are we going to do here? Again, divided in two big videos for consistency's sake. We're going to go through how do ligands bond conceptually, what would be the thing that makes a ligand bond to a metal, and then weighing in on the metal to actually construct an approximation of molecular orbital diagrams for complexes. And this is going to lead us into all the considerations that bring everything together. So starting right off with how do ligands bond, we need to examine the correlations and what can go on. So last week, we landed on the concept of crystal field theory, which demands the splitting of the orbitals from the metal, given this electrostatic interaction with the ligand that will surround the metal. We derived the octahedral and tetrahedral crystal field, but I'm putting here a comparison of all the other crystal fields, also with sort of like an energy scale of the splitting, to not only account for the fact that tetrahedral and octahedral are two boundary conditions, of which the tetrahedral field splitting is very much smaller than the octahedral field splitting, but also to account for what happens in the moment you start to split off these energies even further. You can notice that the splitting here is very highly dependent on the geometry. You do not split orbitals equivalently depending on where are they pointing conceptually. So some of these orbitals, depending on their geometry and how do they lie on a Cartesian plane, are going to be more or less destabilized in comparison to ligands that are taken as point charges. Do we have any evidence of this splitting and the crystal field stabilization energy that comes with it? So this energetic advantage of the metal to bond with a ligand. So the crystal field stabilization energy can be accounted for if you consider the filling of these split orbitals. If we focus on an octahedral field that is going to let us compare things like the aqua complexes, so complexes that would be formed with water and could be potentially formed and split, we can account for what this different stabilization energy would be as we go across the periodic table. So we go from potential D1 metals all the way to D10. We can immediately spot the one in which there is no net advantage because of this 5 electrons and 10 electrons, which is going to half fill or completely fill the shell. These are all considered as high spin. So if you actually do the experimental estimation of the hydration enthalpy in comparison to the theory, whereas the theory is supposed to go monotonically as you go across the periodic table because it's a periodic property, the presence of the crystal field splitting and this energy advantage is going to make so that apart from the one in which there is no crystal field splitting, so D0, D5, and D10, there is no crystal field stabilization energy to bring into the system, all the other systems are going to have some sort of energetic advantage that comes exactly from this crystal field splitting, meaning that this effect must be real. It is not just a conceptualization that we bring into the system. It's something that exists and can be measured as a property. Where do we put these electrons? I mentioned before that we were considering all these complexes before as high spin. The putting of the electrons in considers the concept that the electrons will repel each other. They do not like to be together unless they have to. So in general, if you have two degenerate orbitals, the energy of a configuration in which you're going to cluster the electrons together and leave the other one open is higher than the one in which you put them anti-parallel to each other. And it's even higher than the one in which you put them parallel to each other, occupying both of the levels. This electron repulsion parameter can be estimated as B, which is, if we put it in sort of a wave number type of entity, so it's the inverse of the wavelength, it goes as more or less 1,000 centimeters to the minus 1. This is fundamentally the implication of the hand rule. We want to fill in all the possible orbitals anti-parallel with electrons parallel to each other, because every other thing will be higher in energy. Given this entity of the crystal field splitting, depending on what is your ratio between the delta of the crystal field splitting and the B, you can end up with a high spin complex, just because the delta over B is very small, and the system will always prefer this type of configuration, because pairing the spins will take too much energy, versus an option in which this delta over B is sizable, which means the gap in this energy overrules the energy that will take you to overcome the spin repulsion. So a low spin and a high spin all come down to not just how big is this gap, but how big is the ratio between these two parameters. This is usually estimated with this type of diagrams that sometimes you find completely overgrown, which means if you consider the same system, as you increase the field, so you go from weak field to strong field, so you increase the delta parameter, which tweaks around this delta over B parameter. As this delta over B parameter increases, then you can end up having a spin crossover moment. So for the same, so from free ion all the way to the highest possible configuration of a given ligand, you can have a transition between high spin and low spin. There is a moment in which this thing will go up here, this thing will go like that. They cross over, and if you increase this parameter, at some point you drop into a low spin configuration, even though you started with a high spin configuration or something like that. Is this thing something that we see? Well, even at parity of arrangement of the spins, so even if you consider the same level of spin repulsion, meaning that the arrangement is going to be more or less the same, once again, the effect is actually visible. These energy gaps that you end up having between the orbitals can be experimentally proven, and depending on how big, like what is your geometry, meaning how big is your gap between the energies, you are going to get a different energy to bridge these levels. So you can see how high this gap is with the an octahedral complex. For instance, a completely distorted octahedral complex in which you have this weird gap, one of the signals goes completely off, like it's not even visible, or you can start seeing two of them, multiple of them, depending on how many crosses you're doing. So these things are real, and the jump in energy are different. All of these examples are done with different spin arrangements and configuration of iron too. So it is not down to the metal, it is down to how do you arrange. So you can do these experimental gaps. Note that in the same way we had the T2E, T2GE in the octahedral and tetrahedral crystal field, there are other labels that appear, which is the reason why at the beginning we did not put the symmetry labels. We actually used the actual orbital names to place them in order. I did promise that we will go through what do the labels mean with the orbitals, and the labels fundamentally go as a relationship with the symmetry of your complex. So all of these labels are what are called the Mulliken symbols. So you can label anything with those symbols, but those symbols are giving you the relationship with the symmetry elements of the geometry that you're using. So when we do octahedral geometry, we have an octahedron. Whatever we place in an octahedron must obey the rules of octahedral symmetry. So it's using all of the same symmetry elements that we highlight in an octahedron to be able to say an octahedron is an octahedron. So when you look at the d orbitals placed in this octahedral crystal field, you end up with two sets of species. The EG species is distinct, so it's telling you it's E, so double degenerate, two-dimensional irreducible representation, either on Z or XY. G is telling you that this thing is symmetric in respect to the center of symmetry. So you can only have this G label because the octahedron has a center of inversion. Likewise, T2G is telling you that these three things are triple degenerate, meaning that you cannot distinguish from one into the other. They are equivalent to each other, but they are different in orientation. So you can permute between the three of them, but you must always have three of them. And it's telling you that they're antisymmetric with respect to the C2 axis perpendicular to the principal axis, which is, if you have C4, then you have the C2, and they are antisymmetric because they have this relationship of if you exchange them, then they're different. And you can see that this is also the reflection plane. So indeed, if you switch some of these around, since they need to do this cross, they're not going to look the same. You end up with the lobes overlapping in the wrong direction. And still, you have the G, because this symmetry group and this symmetry arrangement with an octahedron has a center of symmetry. So all of these things can be inverted through the center of symmetry. So you end up having these sets that tell you e.g. T2G. So you can flag immediately where are they coming from, what is their relationship to the spatial arrangement in the complex, which means in a tetrahedral, even with the same orbitals and sort of like a same arrangement of degeneracy, so double degenerate, triple degenerate, you end up with T2 and E because a tetrahedron does not have a center of inversion. So these labels are relevant and they must be changed accordingly as you switch around the possibilities. Now, is crystal field the perfect theory? Would we be having this conversation if you were? So the underlying assumption of crystal field theory is that the metal is left unperturbed. So you are switching the energies, but you're considering that there is no interaction with the orbitals of the ligand. This is not part of crystal field theory as it stands. You do not consider that the ligand is getting affected. You cannot do this in any other way. So there is no mixing with the ligands. You split because they are there as charges, but they do not mix with the d orbitals. If you want to explicitly account for a metal-ligand interaction, you need this coupling with the orbitals. This is a typical thing that builds a molecular orbital diagram. So the electrostatic interaction that you get really has charges with electrons super localized. The electrons of a metal, the electrons of the metal, the electrons of the ligand, and the electrons of the ligand. At best, the bond is completely ionic. If you expand into a ligand field theory in which you consider the interaction between the metal and the ligand, you could have some electron transfer, you could have some electron sharing, which means the bonds can have a different level of covalency. So which orbitals do we use if we want to say that these things must be interacting with each other? We use the frontier orbitals, which is fundamentally the same concept as we floated at the beginning of, or you can consider this as a Lewis acid Lewis base. What a Lewis base and a Lewis acid and a Lewis base do is something that you can see from the molecular orbital, but we need to expand it to be able to say what energies are we pinpointing. So in Lewis theory, you have this thing of, okay, your lone pair is in the sp3 hybridized thing. We go into the p orbital of the other one, and we do this adduct. In this way, we are considering the orbitals as purely atomic orbitals. They are the orbitals of the atom, and the lone pair in the ammonia is exactly equivalent in nature to whatever is bonding to these H's. In reality, if we go and look at the molecular orbital description of this thing, you are basically making the HOMO of one of the molecules, so this one, the highest occupying molecular orbital, the one that contains the lone pair, that we already established is not exactly an sp3, and the LUMO of the other one. You can only have this type of Lewis acid-base interaction if these things overlap in phase. But then from this HOMO and LUMO interaction, you end up having a new version that provides you with a new set of molecular orbitals. Now, these new molecular orbitals actually codify the interaction of this whole molecule, but starting from the molecular orbital of these two. The effect is conceptually more or less the same. But we are doing it now from something that really accounts for all possible interactions and is really truthful to the nature of where is your electron density and what is your electron density doing. From this primary interaction, which is the one that gives the bonding, which is the reason why you use these frontier orbitals, all the others will follow because you clearly sort of pinpoint what is the energy interaction level, and everything else can be scaled accordingly. Remember, this approach is not just for organic or main group type of chemistry. This approach of the frontier orbitals, if you want to see how the Diels-Alder reaction in organic chemistry works and why can you only have certain geometry that work and others that don't, this is actually going with the frontier orbitals. So if you look for frontier orbitals, you're going to find a lot of examples with the Diels-Alder. So it is a type of reactivity that is incredibly relevant and goes across the board. So now that we know that we need to characterize our ligands from the point of view of the frontier orbitals and what the frontier orbitals can do when they interact with the metal, we can start to really put them in categories. The first category we want to account for are the sigma donor ligand. So these are some examples of the sigma donor ligands, the hydride ligands, water, phosphine, like this, something with also a nitrogen atom. Fundamentally, what do? They donate 2 electrons from an orbital of sigma symmetry that is accessible in energy to interact with your metal. This is a typical example of what we were seeing with the ammonia. So ammonia, we've already seen it even in lecture 1, has this lone pair in a sigma type of orbital. So this fits the description, right? So this one is your frontier orbital. This one is what you will use to bond with the ligand, with the metal, sorry. Water will be doing the same thing. So if you see the molecular orbital diagram of water, you have a sequence of possible molecular orbitals that have this lone pair, but this one, despite being its sigma in energy, is too low, so it will never interact because it really stabilized from the interaction between oxygen and hydrogen. The second one can actually go and participate into the bonding. This one is a non-bonding orbital, so this is your sigma ligand orbital. This one is non-bonding, so it does not have a sigma symmetry. Now, if this was with the sigma, you have a second option, which is sigma donor and pi donor ligands. Note that this thing is at the same time. So your ligand is doing both a sigma and a pi interaction. You cannot do a pi interaction without doing the sigma first. The pi interaction that comes from this could come from the lone pair or another set of pi orbitals. So you could have something that is from the, like in the case of any halide with a minus, sulfides, oxides and stuff like that. This could be the lone pair of the electron configuration, or it could be a whole molecule. So you're going to have a pi molecular orbital that has this couple of electrons. Key point here, you are orthogonal in interaction. You do sigma in one direction and pi in an interaction that is orthogonal. You will see it often conceptualized in this way. So you're using both of this, the sigma and the pi, but the sigma is sigma because it's in a direct direction of interaction. So that's the sigma donation. If you go in perpendicular, your ligand still has electron density and your metal is supposed to have something that is compatible. So you're going to give more electron density. So you're going to have another molecular orbital like this and another molecular orbital like this. Your ligand has electron density both in the sigma and in the pi. That's the reason why you can do the double donation. Note on this thing, there are some complexes that are pi coordinated systems. So the pi in your, I'm looking for a sigma donor, pi donor, is in this aromatic arrangement, right? So these type of systems are clarified with this apto interaction. So these apto ligands are the ones that coordinate with the pi donation on a coordinated system. But when you say that I'm doing this interaction from the pi molecular orbital and I'm using that electron density, you're saying that you're not using this carbon or this carbon or this carbon or this carbon. You are using the molecular orbital that encompasses the whole of the molecule with a pi symmetry. So the reason we put the ring in the benzene, for instance, or in any system that you label as aromatic, is because you end up having this coordination like this, but your molecular orbital is sort of like this donut that encompasses the whole molecule. So the formalism of the eta is this type of thing. So you're gonna find these complexes in which it seems like you're bonding to the center of a ring or a center of an aromatic interaction, as opposed to something that is just bonding on one end, like it would be an eta 1, which is the usual arrangement we see. So the difference is that when you say, okay, I'm pointing here in between, it's not because I'm going between the atoms, it's because I'm interacting directly with the electron density of the shared coordinated system. How many electrons are involved in this? It does depend on how many atoms the ring has. So if your amount of atoms, so this one is a pentagon, right? So it's X is odd, then the carbon ligand is usually anionic. So you have 5 + 1 electrons, because you need to consider that there is the additional anionic character. If it's even, then the number of electrons is exactly the same as the one that you have. But you point in the center because in reality, you're pointing towards the molecular orbital of this thing. Third option, since we can do sigma donor, pi donor, there are another class of ligands that can do sigma donor, pi acceptor. So the concept is similar, right? But this time, your pi orbital is accessible in energy and it's empty, meaning that it cannot put electron density in the system, but it can take it from the system. You find it sometimes conceptualized in this way, which is a bit atomic orbital based, but it is the same concept. The sigma interaction goes end-on, so you go directly in interaction. In perpendicular to this interaction, you have an interaction between the pi molecular orbital and whatever is on the other side of the system of the metal. This time, though, your pi doesn't have anything in it. It's empty. So it can accept, but it cannot share something. This is the typical case of like atomic molecular things, H2, N2, O2, they all do this type of trick, but also of very prominent ligands that we already seen in different examples, with the carbonyls, with the cyanides, and stuff like that. And the case as well with some of those coordinated systems, depending on are you empty or are you full. So this apto geometry can be relevant for both of them. So that you need to have this relationship, and in a molecular orbital diagram, which is more proper and correct than this depiction, you're saying this is your sigma donor. So this is the first level of interaction that you do. And this, which is at a different symmetry because it's going to be in perpendicular to this one, is going to be your pi acceptor, because you see it's accessible in energy, but it is empty. So with this accounted for, we know what classes of ligands and we know what features are we looking for in their molecular orbital diagram. In the next video, and for the rest of this lecture, we are going to then account for the full interaction and how to build the full molecular orbital diagram that is accurate for a metal complex.